Bismillahirrahmanirrahim. Welcome students to the online lecture of Digital Logic Design. And in today's lecture, we will be discussing the subtraction process using the complements. In the previous lecture, we discussed the basic binary arithmetics, and we also discussed the method how we can calculate the R and the R minus 1 complement. In this current lecture, we will be utilizing these complements concept to the subtraction part. This part also belongs to the course Learning Outcome 1. For the first part, we will be discussing the subtraction process for the unsigned numbers. For the unsigned numbers, we mean that we are only representing the magnitudes of the number here. We are not representing any sign that they are positive number or the negative number. We are just subtracting the magnitudes. Suppose we are subtracting here two unsigned numbers. Both of them are represented in n digit number, and they are represented in a say base r. R could be used for the decimal, or it could be the for the binary. Most of the examples will be focused on the binary systems. Suppose the m here is the minuend, while n is here the subtrahend. And what we will do is we need to subtract m minus m. But we will be doing it in a slightly different manner now. Because we have discussed the complements, and we discussed that the complements are another way to simplify the subtraction process. So what we will do is that instead of subtracting the number, we will be taking the complement of this subtrahend and we will be adding it to the minuend. So what we will do is, you can say, for subtracting m minus n, we will be actually performing this operation. And if you remember that this Rn minus n is actually the R's complement or the radix complement for the number. So if we just take the complement of that number and add it to the other number, it will give us the same result as we achieve in the subtraction process. So in this way, we will get a very simplified process available for us for doing the subtraction thing. And the other important thing is that because once we are taking the complement part, we will be adding that number. So we will be using the adder for both things, for the addition and for the subtraction. This will be very useful in designing the hardware. Say if we have there are two cases. Say if that m is greater than n when we are performing m minus n. Suppose if the m is greater than n, this will always produce a carry in the result. This will always produce an end carry in the result. For the getting the complete result, what we will do is we will just discard that end carry, and the final result will be equal to the m minus 1. So whenever we have m greater than n, the result will always produce an end carry, and end carry means a carry from the last two most significant bits that we are adding. We will just ignore that carry, and the remaining will be the result of our m minus n subtraction. Suppose if it is the other way around, that m is smaller than n. In this case, we will not be getting any end carry. So this result, this will also tell us that m is also less than n. In this case, what we will do is, because there is no end carry, what we will do is we will take the R's complement of the answer and we will just put a negative sign in front of it. So we will get two different cases here, when m is greater than equal to n and when m is less than equal to n. In both cases, what we are doing is, the process what we are following is that we will be taking the complement of this number n and we will be adding it with the m, and then we will check the result. If m is greater than n, that will always produce an end carry. We have to just ignore that end carry. The remaining part will be the our result. If m is less than n, it will not produce any end carry. So what we will do is we will take the r's complement of the result and we will put a negative sign. Now we will try to discuss these points through certain examples. Suppose first we will discuss the case when m is greater than or equal to n. Say we have two decimal numbers here, which are represented here as this 72532 and 3250. We have to subtract this number from this one. What we do is, because you can see that this is of 4 digit and this is of 5 digit, to make the both of them equal, we will put an extra 0 here. We will put a 0 here. And then we will do is we write the m here as the same one, this. And for the case of n, what we will do is we will take its tens complement. So if we take this tens complement, we will be getting this result here, because if you remember, for the tens complement, what we do is we simply apply either the formula or the thumbs rule, which we have discussed before. We can use either of them to calculate this thing here. This will result in this thing, because if you see that for the last column, when we add them column wise, for the last column when we will add 7 plus 9 here, the result will be equal to 16. So the next one will be the carry, the end carry here. So if we have m greater than n, we have discussed in the last slide, we will just ignore the end carry, or you can say just discard the end carry, and the remaining part will be our result. So in this case, our result is just this term 69282. So if we subtract both this number, we will get this result. Now we will be doing another example, but this time for the binary system. Suppose we have two binary number, x and y, or you can just call them m and n. We need to subtract x minus y. So what we will be doing is we will be taking the 2's complement of this y. So first we will write x here as this one, and when we are going to write the y here, we will be actually taking its 2's complement. And if you remember that we will change all the least significant zeros till we have the first one, because in this we have the first one here, we will write the first one here as the same, and after that we will just interchange all the bits, change 1 to zeros and zeros to 1. And now because we have taken the complement, we will be just performing the addition. So now if we add them, then the similar the standard process of addition, the column wise operation, this will give us the result. We will have to just add them column wise, just like this. 0 plus 1 will give us 1, 0 plus 0 will give us 0, 1 will give us 0 here, and it will give us 1 carry. So in a similar way, as we have performed the addition in the last lecture, we will add both of these numbers. This will produce a result of this one. Again, for the last digit, we will get an end carry of 1 here, because as we have discussed in the last slide, if we get a end carry, we will just discard that end carry, and the remaining part is our result. So x minus y, this is our final result. So you can always check that, you can convert them into the decimal and then check that the result is equal to this or not. So this was the first thing, in which we have a condition in which m was greater than or equal to n. So we discussed both examples, one for the decimal system and one for the binary system, and both of them, because m was greater than n, we got a end carry, and we have to just ignore the end carry, and the remaining part is the result. So this was the subtraction for two numbers in the unsigned case. Now we will be discussing the next example when m is less than n. We have taken the same two numbers here, but this time we are subtracting it from different perspective. Now we are doing this number minus this. So first we have written here m, here is this. We will take the tens complement of this, we can easily calculate that. We have, you can use the formula or the thumb rule. Just subtract the first number from the 10 and the rest of the numbers from 9. We will get this as the tens complement for this number. And now we have to perform the addition instead of the subtraction. So we will apply the normal decimal addition to this part. In this case, when we will add all these numbers column wise, we will get this result. In this case, there will be no end carry generated because m is less than n, so there will be no end carry generated. So when there is no end carry generated, we have to take the tens complement of the answer. So what we do is we take the tens complement of the answer and put a negative with it. So we take the 10 complement, so its 10 complement is this, and we just put a negative sign here. So this is our final result in this case when m is less than n. Now we will be discussing a similar example for the binary system. Suppose we have the same two numbers x and y, which we discussed in the last slide, and now we will be representing them we will be subtracting them using the 2's complement representation. For the 2's complement representation, this is y. Now we have to perform y minus x, which would become equal to y plus the complement of x. So we perform the complement operation for this one. We will get the result here. We have you can use the formula or the thumbs rule, whichever you feel convenient. This is, and now we will just add these two numbers. We will add them in the same way that we have any binary numbers column wise. This will give us the final result. Again, there is no end carry generated, means from the last two bits there is no carry generated, so there is no end carry for this system. And the answer is calculated by taking the 2's complement of this number and putting a negative sign with it. So if we just take the 2's complement here and put a negative sign here, we will get this result. So we have seen that two different parts for the unsigned number when m is greater than n or when m is less than n. We have utilized the complements part here, that when we are using the complement procedure, we can just simplify the subtraction part by just taking the complement of the number which we want to subtract and just add that number to the other number. This will result in the subtraction process. We have to check the results in the last step. If there is an end carry generated, we need to ignore that and the remaining part will be the result. If there is no end carry generated, then in that case we have to take the r's complement of that number and put a negative sign with it. So this results in this. Now we will be discussing this example with say r minus 1 complement. We have discussed the few examples in the last two slides which were with the r's complements. Now we can also do the same procedure with the r minus 1 complements. If the sum is less than 1, the correct difference when an end carry occurs. So if we remove the end carry and add 1, the sum is referred to as an end around carry. It's just the same thing, because you know that the difference between the two complements, the r and the r minus 1 complement, is of the 1. So if we get an end carry, what we do is just we ignore the last carry and we add our 1 in the remaining part, which will give us the correct answer. We will see a few examples of this here. Say we have two numbers x and y here. We will take the complement of this y here, which will 1's complement here. 1 complement is very easy to calculate because we have to just reverse all the bits. So we have instead of the 2's complement here, we have calculated the 1's complement. So 1's complement is just reversing all the bits of this, so which will give us this, and then we will just have to add them column by column, which will give us this result. So this is our result here. In this case, you can see that there is a carry of 1 generated here, and carry has been generated here. So we have to perform this end around carry, which means we have to ignore this one here and we have to add 1 here. So the final result is this one. Why we have added 1 here? Because we are dealing with the ones complement, and the difference between the ones complement and two's complement is a value of 1. So what we do is we just ignore the last carry bit, and what we do is for the remaining part we will just add a 1 here. So this will give us the complete or the accurate answer. This the x minus y is now determined as this one. And now if we, for the same numbers, if we do this y minus x term here, what we do is we will be calculating the ones complement of x this time. So it's again just reversing all the values of x here. We will get this result here. If we just add them now, because we have taken the complement, we will just add them instead of the subtracting. We will just add them column wise. This will give us this result. In this case, you can see that there is no end carry generated. In the first example, we have an end carry generated, and what we did was we ignored the last end carry and we added the 1 here. So in this case, what we do is that we take the ones complement of the answer and put a negative sign with it. So what we do is that we will take the ones complement of this and put a negative sign here. So we have just taken the ones complement of this thing here, and we also put a negative sign. So this is the end result. So we have seen two different methods of utilizing the complement in a subtraction process. One is with the r's complement, and other is with the r minus 1 complements. Both of these are for the unsigned numbers. You can always do the same process with the previous ones, which we utilizes the with r's complement terms for both the decimal and the binary system. We are just trying to discuss both the number system decimal and the binary here, because decimal is our general intuitive thing, because our common day understanding is in the decimal, while the binary is the one which is implemented in the hardware. So we are trying to look at both of the things, but the important thing with respect to the hardware implementation is this binary thing. Now we will discuss the signed binary number system. So far what we have discussed is that we are subtracting two number with some magnitudes. We haven't said that any number is positive or any number is negative. We are just subtracting two numbers. So in this case, now we need to define a number with a certain sign. Either it could be positive or it could be negative. Because we have seen that there are a lot of process or things involved in the unsigned number. Because in the unsigned number, if you have seen that if there is no end carry generated, then what we do is we take the r's complement of the answer and we add a minus sign with it. But how do our hardware interpret this negative sign? We need to design a certain mechanism through which our hardware system could recognize that either this system is this number is a positive number or this number is a negative number. So there is no separate thing that a negative or plus sign could be interpreted in hardware. It could be interpreted in a form of only the bits if we define certain bits, because on a bit can a value of a 0 or 1. So what we do is we define an extra bit in the most significant location, and what we do is that if that bit value is equal to 0, then we say that the rest of number is positive, and if that most significant bit value is equal to 1, then we say that it represents any negative number. The rest of the bits represent the magnitude. The most significant bit will represent the sign bit. So in this way, we represent any given number in the form of a sign bit. The sign bit location is always the most significant bit. We will try to understand it through a very important table. This is table 1.3 from the book. It defines given decimal numbers into equivalent of sign 2's complement representation, sign 1's complement representation, and a sign magnitude representation. Generally, first for the understanding, we will just be using this thing, the sign magnitude thing. In the sign magnitude thing, what we do is Suppose we have any given number of this is decimal equivalent. What we do is we reserve a single bit. Say this is we are representing this any number in the form of 4 bits. What we do is we represent this MSB. This is the MSB here, and this is the least significant bit here. For the MSB part, what we do is we reserve a bit here, MSB, and this bit is here is representing the sign of the number. If this bit value is 0, it will be representing a positive number. If this bit value is 1, it will be representing the negative number. And what we do is that the remaining 3 bits will be representing the magnitude. So for example, if you see this +7, this is representing the +7 in sign magnitude form. The 0 is representing that it is a positive number, while 111 represents the magnitude of 7. So this represents a +7. Similarly, if you look at +5, the 0 represents here that it is a positive number, and 101 represent here that it is magnitude is 5. For the negative number, what we do here is that the first bit represents that it is a negative number, and while the remaining 3 determines that what is its magnitude. So in case of say 5, 1 is negative here, and 101 represents the magnitude of 5. So this represents -5 here. If you represent it that way, you can see that you have to represent 0 in a 2 different way, because there's a +0 and -0. +0 will be represented by all zeros, while -0 is represented by 1 triple zero. So this doesn't seem to be a very good way to represent a zero thing or zero quantity here, because we have a separate negative 0 and a separate positive 0, but both of them have actual magnitude equal to 0. So what we do is we use another common representation for this assigned binary system, which is known as the signed 2's complement representation. This is the most common way or the standard way of representing the binary numbers or the signed binary numbers. In this process, what we do is that we use the 2's complement representation to determine the negative equivalent. The positive numbers remain the same. If you see that for the first column for this part, all the positive number from 0 to 7, you see that this and this, all these numbers are the same. It means that the representation of all the positive numbers are same for the sign magnitude term and the sign 2's complement term. But the thing that changes is for the negative number. For the negative number, what we do is that we just take the 2's complement of this positive term here. Say for this one +1 here. If we take the 2's complement of this number, what we will do is that we will the first one will remain the unchanged, while all the remaining bits will be reversed. So it will make it all ones. So this is -1 here. So if we have to represent say +5 here, which is represented here, we just take the 2's complement of +5, we will get this 1011 here. So we represent the sign 2's complement representation in this way, that we know what are all the numbers in the positive half, and we will just take on the 2's complement of that number. Suppose if we have given in this number, you can see that from the first bit you can also recognize that bit is positive or not. The same thing which we have done here. For all the positive numbers, this first bit, the most significant bit is 0, and for all the negative numbers, this bit is equal to 1. So which is also representing that these are the negative numbers and these are the positive number. Suppose if we have this number -4 is represented here as 1100. We know what is the original magnitude of this one. This is representing the -4 term. So what we do is, as we have discussed before, that if we take the 2's complement again of a number, it will result in the original number. So we will get for that the first zeros and 1 will remain the same. We will get 0 0 0 1 here, and we will get 1 here. So this is, we will get that number here. So This is the most standard way of representing these signed numbers, which we say are represented in signed 2's complement form. This is also used, but it also have many limitations, mainly because of this plus 0 and the minus 0 terms. And also we also have to separately deal with the magnitude and the sign bit separately. But in this case, we can combinedly use all these all this process addition and the subtraction process by using this complements part. We don't have to worry about the magnitude part separately and the sign part separately. Now we will be discussing a few examples that how we can use this sign 2's complement representation for the subtraction process. Say we have two signed binary numbers where we want to subtract these numbers. What we will do is we will just take the number which we want to subtract, take the ours complement of that number. If a carry out is generated, we will just discard that carry out, and the remaining part will represent the result. The carry out will always be generated from the sign bit, because the sign bit is the most significant bit. This would also simplify the over subtraction process, because if you see that these two are the examples of a common subtraction. Say we have any number and we have to subtract with different numbers. Say this is a minus b, this is a minus b. So we know that for any term, if we want to calculate this term, we can convert it into an addition part. How? Because if you have seen that from the table of the last lecture, the plus b's value represent the positive number, while the minus b is representing its 2's complement. So we can always represent, instead of and subtracting them, we can always represent that b in form of its 2's complement, and then we can add it with the original number. So what we do is they just take the 2's complement here, which is represented at here, and similarly for this term here we will apply the same thing. We will change this operation to the addition front, and we will take these 2's complement here, which will result in the original number, and the positive number which will be represented here as this one. So in this way, what we are doing is we are effectively taking a single process of addition for doing both the subtraction and the addition process. Now we will discuss it through certain examples. Suppose we have these two binary numbers. We need to add these numbers. We are just adding these numbers. What we do is, because both of them are in the signed representation, so we need to represent in a form of plus 6 plus 13 or minus 6 minus 13. We need to represent a sign here, and the most significant bit should represent the sign here. So first what we do is we should make both of number of the same bit. How we do it? Say 6 is represented as 110, while for the 13 we have to present only we are talking about the magnitude only here. The 6 magnitude is represented as 110, while the 13 magnitude is represented as 1101. So it means that the higher number of bits are required by the 13. So what we do is, first we put an additional 0 here to make both of the magnitude equal to 4 bits. So now the magnitude of both bits are here equal to 4. Then what we do is we put an extra bit to represent the sign here. We will add an extra bit here, 0 here, and extra 0 here. This will be representing here the sign. And because we know that if we are adding the two n bits, our result, it can be in n plus 1 bit, a maximum of n plus 1 bit. So we need an extra bit to represent our result. So that's why we have added an extra bit. So in this way, first we define the number in a very specific number of bits that should be usable for us. So first we defined 13 was represented in 4 bits. The next bit was added because of the sign, and after that next bit was added because the result can be in n plus 1 bit. Same was case for this one. And now what we do is we simply perform the addition part. For clarity or check, we have also done the decimal part here. We have done this similar part many times. We will keep them adding column wise, which will give us this result, which is equal to plus 19, and this is quite clear from this decimal part too. Now what we are doing is now we are adding two numbers, but this 6 is now minus 6. Instead of the plus 6, we have the minus 6. So what we do is we will just take the 2's complement of this. We will just take the 2's complement of this number. So taking its 2's complement will give us this number. This remains the same, and now we will just add it, and it will give us this result. This will give us a value of this. Sorry, there is one here. Actually, it's 1. Yeah. So we will get this result, which is equal to plus 7. We can clearly see that minus 6 plus 13 will give us this result. And now in the next case, what will we do? We have minus 13 term and the plus 6. In this case, we have minus 6 and plus 13. Now we have the plus 6 and minus 13. So what we will do is we will simply add them column wise, and the final result here is represented as this minus 7. So this is basically the, if you take the 2's complement, it will give you plus 7. So we will get the minus 7 result here. This result is automatically in the 2's complement or this 2's complement form, and we have 1 1 1 0 1 here, and if you can see that there is an addition, there is this result is in the complete this form, that the final you have add 0 1 here, 1 1 will get 0 here, and it will give us a 1 carry around here, and that will again result 0 here, and that will be transformed here, then here and here. So we will get this result here, and you can see from the result, because the most significant bit is 1, so it is representing a minus number. And next is the last one is that we add minus 6 and minus 13. So both of them, these numbers are negative now. Both of these numbers are negative now. So that would result in a negative number minus 19. It is very clear from the decimal part that it should result in a negative number. So if you see this, we will have a result here as this. This first bit, or the most significant bit here, represents that this is a negative number. So if we take the 2's complement, it would be equal to 19. In this case, an n carry is generated, but as we have said that if any n carry is generated, we will just ignore that. So remaining part is the result. So this is the minus 19. So in this way, we will use the signed 2's complement representation to add or subtract any number, because now we have all the numbers with certain sign, either it's plus 6 or it's minus 6, either it's plus 13 or minus 13. So we just need to convert the number which is in the negative into the 2's complement equal and add it with the other number. The result which will give us will tell us that the result is either positive or negative. We can just check it through the last bit. If this MSB is equal to 0, it will tell us that this is the positive number, while if this is 1, it will tell us that this is the negative number. In many cases, say for this one, say plus 6, what we do is if we are representing plus 6, we have to represent it in say 8-bit, 9-bit or 10 bits. Generally, it can be represented in a 4-bit form. So suppose if we have to represent it in a 10-bit, then what we do is we keep on adding the zeros here. So if we have any number in its 2's complement form, like say this or this, what we do is if we have to represent this number in say 10-bit form, what we do is keep on adding 1 in the most significant bit. It is equivalent to adding zeros in the original number. So if we have a number in a 2's complement form, what we do is if we have to add extra bit, instead of zeros we add 1 or the last significant bit in that case. Kindly do read these pages from the book. Thank you.